Morning, students.
Good morning, ma'am.
Morning. Today, I'm going to recapitulate the solid state unit. So just listen carefully. If any question, then you can ask. Now, solid state. We say the solid is what? Solid is something where particles are very closely packed, or you can say they are held together by the strong intermolecular forces. Now the building constituents have the fixed positions and they can only oscillate about their own position. Means that if this is your solid and this is your particle, it is going to oscillate at its own position only. It cannot move here and there and oscillate at any other position. Due to which we say that they have the definite shape and definite volume. Compressibility, you cannot, if you are going to take a solid, you cannot compress the solid. Further, we say that the solids, they can be classified into the two. One is your amorphous and another one is your crystalline. Now, in case of amorphous solids, when we talk about the amorphous solids, the arrangement of building constituent is not regular one. It is not regular. They may have a short range order. Their melting points are not going to be sharp. They are isotropic in the nature. Now, what is the isotropic? Isotropic in the nature means over here their properties like your mechanical strength, electrical conductivity, they are going to be same in all directions. For example, your quartz, glass, your rubber, etc. When we talk about the crystalline solids means the arrangement of building constituent is regular throughout the entire 3D network. A crystalline solid has sharp melting point and is anisotropic in the nature. Means their physical properties like your electrical resistance or refractive index, they show the different values when measured along the different angles or directions in the same crystal. They have the definite geometrical shape with the flat faces and the sharp edges. For example, your quartz and NaCl. On the basis of this, we can expect the one question for the 2 marks over here. That is the difference between amorphous and crystalline solid. Now, further moving ahead, we can have the different type of the solids. Now, different type of the solids can be what? The first solid can be your molecular solids. Molecular solids can be further classified as the nonpolar, polar, and hydrogen bond. In these molecular solids, as the name only implementing over here, therefore the constituent particles will be the molecules. If we talk about the forces, the bonding or the attractive forces, then in this case the force will be the dispersion forces, or you can say London forces over here. In the case of non-polar, dispersion or London forces. When we talk about the polar, polar means that there will be the development of the poles, therefore the force will be dipole-dipole. And when we are talking about the hydrogen bonded, then of course there will be the attractive force of the hydrogen bonding. Now, if we talk about the physical nature, these both will be softer in the nature and it will be hard in the nature. Electrical conductivity, if you're going to look, these all three are going to be insulator, and in this case we should know at least two examples each. Like in the case of non-polar, you can take a CCl4, H2, I2, CO2. There is no development of the poles. In the case of polar, you can take any one having the development of the poles, means one of the atom is the electronegative in the nature, like your HCl, SO2. And in the case of hydrogen bonding, your H2O. Next type of the solid is ionic solid. Now, when we talk about the ionic solid over here, ionic solid means what? That in the case of ionic solids, there will be the ions. Just a second. In the case of ionic solids, there will be the molecules or the constituent particles will be the ions. And if we talk about the attractive force, then it will be a electrostatic or Coulombic forces. Now, they are going to be the hard and the brittle in the hard, but brittle in the nature. They are the insulators in the solid state, but they are the conductors in the molten state as well as in the aqueous solution form. For example, NaCl, magnesium oxide, zinc sulfide, calcium fluoride. Another one, that is your metallic solids. Metallic solids are what? They have the positive ions in a sea of delocalized electrons. They have the metallic bonding. They are hard but malleable and ductile. They are conductors in the solid as well as the molten state. For example, is your iron, copper, silver, magnesium, etc. Fourth one is your covalent, or you can say network solids. In this, we have the constituent particles as the atoms. They have the covalent bonding. They are the hard as well as the soft. For example, your diamond and graphite. They can be the insulators, and in very exceptional cases, they can be the conductors also. Now, from this complete different types of solid, we can expect a reason assertion question or a multiple choice question for the 1 marks each. Another thing, that is your space lattice and unit cell. Now, when we talk about the space lattice is the three-dimensional arrangement of identical points in the space which represent how the constituent particles are arranged in a crystal. For example, this is my lattice structure. So this is basically what? This is basically a 3D structure in which it is having identical points in the space and each point is representing the constituent particle. Now, when we talk about the unit cell means that it is the smallest portion. Like अब ये पूरा complete एक cube है, इस cube के अंदर भी we are going to have the different further cubes. So that a unit cell is the smallest portion of a space lattice, which when repeated in the different directions going to generate a entire lattice. This will be your counted as the entire lattice. Now, this unit cell is characterized by the 6 parameters. that is the axial angle. Axial angle will be your alpha, beta, and gamma, and axial lengths will be the A, B, C. Means over here, if I want to represent, then it will be having this alpha, beta, gamma. Similarly, A, B, C. These will be the lengths. Now, further we have the crystal system. Crystal system is what? On the basis of the axial distance and the axial angles between the edges, various crystals are divided into 7 systems. That is your cubic, tetragonal, orthorhombic, or you can say it as a rhombic, hexagonal, rhombohedral, monoclinic, or a triclinic. Now, in this case, cubic, we have the primitive, body centered, and face centered. Primitive, body centered, and face centered. In the case of tetragonal, we have the primitive and body centered. In this, we have the primitive, body centered, face centered, and end centered. Then we are going to have the primitive, 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 and end centered, and primitive. Now, talking about the cubic, we say over here all the 3 axial distance are equal and all the angles are equal. In the case of tetragonal, your 2 angles are equal and 1 angle is different. Distance, and all the 3 angles are going to be same. In this, all the 3 distances are different, but all the angles are going to be same. In this, 2 distances are same, 1 distance is different, 2 angles are going to be 90 degree, 1 angle is going to be 120 degree. Similarly, in the case of rhombohedral, all the 3 distances are going to be same. Alpha and beta are going to be 90 degree, but gamma is not going to be 90 degree. In the monoclinic, all the distances are unequal. Alpha and gamma is going to be 90 degree, beta is not going to be 90 degree. And in triclinic, all the distance and all the angles are going to be different. Now, in all these cases, we should learn at least 2 examples each in this case, as a question, numerical based question can be asked over here. Next is the number of atoms in the unit cell. When we talk about the number of atoms in the unit cell, we say an atom lying at the corner of a unit cell is shared equally by the 8 unit cells. Means आपका कोई भी एक cell है, this is your crystal. Now this is your 1 unit cell. This particular unit cell is going to shared by or equally by all the 8 unit cell. Therefore, we say that only 1/8 of an atom belongs to a given unit cell. अगर मैं इस unit cell की बात कर रही हूँ, तो इसका जो particle है वो 1/8 ही यहाँ पे share होगा. Another thing, the atoms present on a edge is distributed among the 4 unit cell. Therefore, it will be 1/4 of an atom belong to given unit cell. Then, if you are having the face centered, then 2 edges in unit cells. So it means half is going to lie on each face. Then in the case of body centered, in the body centered, your entirely belongs to 1 unit cell. It is not shared by any other unit cell. Therefore, if we are having a simple cubic, in the case of simple cubic, it will be 8 into 1/8. That is your 1 atom. In the case of body centered, it is 8 into 1 by 8 plus 1 is present at the body, this. Therefore, it will be 2. If we talk about the face centered, then 8 into 1 by 8 plus 6 will be present at the face, but half is going to share. So it will be equal to 4. So this calculation we should know. Another thing, if we talk about the density of the unit cell, then the formula for the density of the unit cell is Z into M divided by A cube multiplied by NA, where D is the density. Over here, A is given in the centimeter, M is the mass, and your Na is the Avogadro's number. Besides these, we have the other parameters also, like your atomic radius. Simple, you have to learn the formula. If you are talking about the simple cubic, then your radius will be A by 2. If you're talking about this time I gave the question also BCC, then your radius is equal to root 3 A by 4. If we are talking about the FCC, then R is going to be A to root 2. Now coming to the coordination number. Coordination number in the case of the simple cubic will be 6, BCC 8, FCC 12. All these calculations and detail we have already discussed. It is a recapitulation, so I'm just sharing the values. Coordination number basically is what? It is the number of nearest neighbors that a particle has in a unit cell, and it depends upon the structure of unit cell of the crystal. Further, we have the packing efficiency. When we talk about the packing efficiency, it is the percentage of total space filled by the particles. So packing efficiency will be what? It is the volume occupied by atoms present in a unit cell divided by the total volume of the unit cell multiply by 100. Now, if we talk about the packing efficiency in the case of the simple cubic, from all these, we expect a numerical based question. So, packing efficiency is single cubic. On calculation, it comes out to be 52.4%. If you are having a CCP and HCP, then that is your what? Cubic close packing and hexagonal close packing. It comes out to be the 74%. In the case of the body centered packing, it comes out to be the 68%. Now, close packing of the constituents. Now, close packing of the constituents, if we talk about in the one dimension means they are arranged in such a manner in a straight line. If we talk about the two dimension, then they are arranged by stacking, or you can say the rows of close packed spheres. Now it can be hexagonal or the square, like we are going to have this. Now if I say about the square, so means what? It would be like this, square closed packing. But in this only, if I talk about the your, now over here if you look, that after each sphere there is the another sphere. But if I talk about the hexagonal, now in दोनों के void space में your another one is going to come. This. Now talking about the hexagonal, what is there? in this manner. This will be your hexagonal close packing. Similarly, we are going to have the three-dimensional structures also. On the basis of this, we have the voids, and we can have the two types of the voids. That is your octahedral void and a tetrahedral void. If we talk about the octahedral void, then this type of void is surrounded by the six spheres and formed by the combination of two triangular voids of the first and second layer. But when we talk about the tetrahedral voids, they are surrounded by the four spheres which lie at the vertices of the regular tetrahedron. Now, on the basis of this, further we can have the crystal defects. Now, when we talk about the crystal defects, they are basically what? They are the irregularities in the arrangement of constituent particles. So, broadly, crystal defects are of the two types. That is your point defect as well as the line defect. When we talk about the point defect, in the case of the point defect, we say that when we are talking about the point defect, there are the irregularities or the deviation from ideal arrangement around a point or an atom in a crystalline substance. Whereas when we are talking about the line defect, there are the irregularities or deviations from ideal arrangement in entire rows of lattice point. These irregularities are called crystal defects. Now, in the case of the point defects, we have the interstitial, means atoms or ions which normally occupy voids in a crystal. Another one is vacancy, means when one constituent particle is missing from the crystal lattice, means कोई खाली जगह वहां पे unoccupied position रह गई हो. This point defect can further be classified as the stoichiometric, impurity, and non-stoichiometric. Now, when we talk about the stoichiometric, the point defects that do not disturb the stoichiometry of the solid, means uska jo bhi ratio hai, that is not going to be disturbed. Now, when we talk about the vacancy, means a space is vacant over here. In the case of interstitial site, the crystal is said to have the interstitial defect. Due to it, this defect, density of the substance increases. Now, further, we say that ionic solids have these defects as the Schottky or the Frenkel defect. In the case of Schottky defect, the defect arises when equal number of cations, Schottky defect, equal number of the cations and anions are missing from the lattice. In the case of the another defect which takes place in the ionic solids, that is your Frenkel defect. In this, it arises when some of the ions of the lattice occupy interstitial sites, leaving lattice sites vacant. Further, we have the impurity defect, means in the place of the some other cation, another thing has been, another cation has came over here. Like अगर NaCl का कोई crystal है तो उसके अंदर strontium आ जाए, replacing the sodium. So that will be your impurity defect. Non-stoichiometric defect means that arise when the stoichiometry of a substance is disturbed. Like if your metal has become in the excess or metal has become a deficient. Further, we have the in this magnetic moment. Magnetic moment is what? It is the magnetic properties of substances which results from their magnetic movements. Now, further in this, the doping or the electric properties for this particular year, it is being deleted. So we are not going to discuss it further. With this, we finish our unit for this particular year. Now, basically, what type of the questions we can expect from here? The very first important question which we can expect from here is the numerical based question. A numerical based question is a 100% question which we can expect from here. It can be whether you have to calculate the formula, or you have to calculate besides the formula question can be of the 2 marks or 1 marks. Then you can have the determination of the formula only in a higher marks also. Then you can have the uh, shape of a crystal, that whether it is a face centered or it is a body centered. Then you can be asked to calculate the density or the volume. After this, we can have the question based on the reasoning. Reasoning question is what, like for example, shortcut effects lower the density of related solids. How? Then conductivity questions conductivity is being deleted. Then, like this time I gave you a question providing a picture and asking you which type of defect is being represented in a given picture. What will be the formula for the radius? What will be the calculation for it? Such type of the questions can be asked over here. With this, we finish our solid state. Disha,